going to be looking at learning target number 2, which is transformations of functions. So as I stated before, this is the only thing that you will be assessed on from Unit 2 is transformations of functions. So folks, we're going to do kind of our flow chart or our kind of, key information for this on page 5 down at the bottom. So this is for section 2.1, transformations. And again, all of this information is contained in your note packets as well. I just kind of wanted to do a little bit of graphic organizing for you guys so you have it in one place and just as a nice refresher that we can review together. So in order for us to do transformations, yes, you now have your calculator as a way of checking your graphs, but I'm going to be looking for very specific work as far as you being able to do your transformation rules and what you know about your parent functions. So the first thing we're going to cover is the 5 types of parent functions that we looked at in this unit. First, the linear function. What does it look like? Y equals x. Up and to the right with that positive leading coefficient. The domain is all real numbers, and the range is all real numbers. Now, you can use interval notation, but please, 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 folks, if you are using interval notation, make sure that you understand the difference between a bracket and a parenthesis. And same with inequality notation, make sure you understand the directions of the signs. So those are our key features for the linear function. I also want you to write that the y-intercept is at 0, 0. Normally, we don't generate the parent table for this because the linear functions are fairly easy to graph using good old slope-intercept forms. So linear functions are the first of our parent functions. Our second type of function is the absolute value function. Which is a v. Y equals the absolute value of x. That's what the equation looks like, and the graph looks like a v. Now, for this one, we need to know how to generate the parent table. Does anyone remember what we used for the inputs of the parent table on almost all of these? -1, 0, and 1. These are nice, easy, small values to pick, and they also span the negatives and positives, and 0 is almost always the vertex, the central point, or the starting point. For our linear function, 0, 0 is our starting point, our y-intercept. For the absolute value function, our vertex is at 0, 0. So as long as I know those inputs and I can plug them in, the absolute value of -1 is 1, absolute value of 0 is 0, absolute value of 1 is 1. Our domain is all real numbers. And our range, in a general sense, it's y greater than or equal to the vertex y value, or if it has been transformed in some way, it could be y less than or equal to. But it is dependent on the vertex y value. And that's parent function number 2. Next up, the quadratic function. Now, at this point, you're probably the most familiar with the quadratic just because we've spent the last couple of units graphing them, but you need to know how to use our transformation rules, and this is nice because we reviewed this again with vertex form. So quadratics look like use y equals x squared is the equation. Now, the parent table for this one, it looks exactly the same as the absolute value function, which is why sometimes with quadratics, we tend to go a few points further. You don't have to do this. Just make sure that when you're graphing those quadratics, they definitely look like a U, and you don't make them too pointy as a V. Then when we plug those values in, -2 squared is 4, -1 squared is 1, 0, 1, 2. With the vertex being at 0, 0, just like the absolute value. Our domain is all real numbers again. And our range is exactly the same as the absolute value, where it's y greater than or equal to the vertex y value, or less than or equal to, depending on if it has been transformed in some way. Our next parent function is the cubic. Now, if you're looking at that cubic equation going, oh, I know it's a weird little squiggle, but I'm not sure which side it goes up on and which side it goes down on, the best way that you can figure it out is by generating the parent table. So same inputs, -1, 0, and 1. And when I plug those in, what's -1 times -1 times -1? -1. 0 cubed is 0, and 1 times 1 times 1 is 1. So if I were to do a happy little graph of those points, -1 would be here, 0, 0 would be here, 1, 1 would be here, and hopefully that's enough of a refresher that we should be curving up through this point and curving down through that point. So the cubic graph is a little bit tricky. It needs to curve up from 0, 0 and down from 0, 0. So that center point, it's not really the vertex. I normally put a C for central point, but if you want to call it the vertex, you can. Now this one has a domain of all real numbers and a range of all real numbers. Cool beans. And that is the last of our kind of parent functions that have the most in common. Notice that all 4 of these that we just looked at have a domain of all real numbers. The 5th and final one is the only one that doesn't have a domain of all real numbers, and it also has a different looking set of values in the parent table. Does anyone remember what that last function is? The square root function. So we're going to put the square root function up here, off doing its own thing. So up at the top here, square root function. Now the square root function has an equation of y equals the square root of x. It starts at a vertex and curves outward and to the right as long as it has not been transformed in some way. The parent table is the only one that doesn't use -1, 0, and 1. Folks, why can't we use -1 for an input? What's the square root of -1? It's I. So now that we've done that work with simplifying using the quadratic formula, we have a better understanding why we can't use -1 here. When we get the imaginary unit, it doesn't show up on our graph. So we are going to start our table with 0, which will be our vertex. And then our other inputs will be 1. And what about for the third one? 4. We're going to use those perfect square values. So the inputs are different for this one. Square root of 0 is 0. Square root of 1 is 1. Square root of 4 is 2. The domain is x greater than or equal to or less than or equal to the vertex x value. And the range is y greater than or equal to or less than or equal to the vertex y value, depending on if it has been transformed. And that is our 5th parent function. So what you need to know, like be sure you know for this section, is the parent tables. That is going to be required work when you are showing how to transform these without using your calculator. And when I say without using your calculator, you can still use your calculator. It's just you need to show me that you didn't just use your calculator or grapher, that you actually know how to make the transformations work with the table. So that's where we get into our transformation rules. Inside transformations affect x. And you might want to cross your eyes there because it's those transformations that do the opposite of what we would think in regards to the sign. The outside transformations are the ones that affect y, and those signs are consistent with what we would expect for the sign. So inside transformations, opposite of what we would think. Outside transformations, consistent with the signs. So what we are going to do, folks, is we are going to... You can cross number 11. I'm not going to do that one. And I want you to flip back a page, and we're going to do number 7 together. And I'm going to be explicit with the work that I am looking for, not only in this packet, but also on the test. So, number 1, you need to describe the transformations. This is going to be important for partial credit. Did you find all the transformations? Did you describe them correctly? Because that's going to be part of showing mastery on this content. Step number 2 is you must show both the parent and the transform table. You only have to graph the transformed points, but you might find it helpful to graph those parent points as well, just to make a comparison and say, does it actually match what I said it was trying to do? So describe your transformations, show your parent and transformed table. So we're going to go ahead and go through number 7 together. Now, how I would start this problem is look at it and say, what type of parent function am I dealing with here? That is an absolute value. Now, it isn't the parent function. It has been transformed in some way. So my actual parent function looks like y equals the absolute value of x. So that's the parent function. And now we are going to make the parent table. So using those 3 good values, -1, 0, and 1, we get 1, 0, and 1. Now, you don't have to plot these points, but I think it's helpful. That way you can compare your transformed graph and say, is it doing what I said it was doing? So there's our plain old regular absolute value function. So now what we are going to do is we are going to look at the equation and describe what each of those numbers is doing to our parent function. Let's see what we remember. What's that -5 on the outside doing? Down 5. That -4 on the inside, cross our eyes, it does the opposite of what we would expect. That's going to move us right 4. So outside transformations move the y's up and down, and then inside transformations move left and right. Negatives move us to the right 4, and down 5 goes down 5. Now what about that 1/3? That 1/3 is being multiplied on the outside. Those multipliers will be a stretch or a shrink. Since this is a fraction, it will be a vertical shrink by 1/3. So we have now successfully described all of our transformations. I will say that back on the original assessment for this, one of the bigger mistakes is students forgot the 1/3 altogether. So that's why I do recommend that you describe the transformations first. That way you can make sure you transform that parent table using all the transformations. So those outside transformations, or the y stuff, is going to affect our y's. So I'm going to need to move my y values down 5 and vertically shrink them by 1/3. How we do that is kind of exactly how it appears in the equation. I'm going to multiply my y values by 1/3, so 1/3 times y, and then I'm going to subtract 5. Following PEMDAS, I'd multiply and then subtract. Now for my x values, how am I actually going to move them right 4? This is what's weird. We are going to add 4 to the y values. So it should look a little familiar though, because isn't this what our h and our k values did in vertex form? Our h value always switched signs from the equation to the coordinates. So if it's -4 in the equation, it's +4 when we actually do the algebraic transformation. And now we're going to do it. We're going to apply those transformations that we wrote to our parent table. So if I add 4 to all of those values, reminding myself that 0, 0 is the vertex, -1 plus 4 is 3. 0 plus 4 is 4. 1 plus 4 is 5. Now the y values are not quite as friendly. So if I multiply 1/3 times 1, I get 1/3. If I subtract 5, I get -4 and 2/3. You can use your calculator on that. You can turn it into a mixed number. You can look at what the decimal version would be if you want to approximate it for your graph, but anything is okay for that portion right there. And then if I plug in 0, 1/3 of 0 is 0, and then -5 is -5. We take 1/3 of 1, it's 1/3. and then subtract 5, that's negative 4 and 2/3 again. And now these are the points that I'm going to plot for my transformed absolute value graph. So forward 3, down 4 and 2/3, awkwardly close to negative 5 there. And then 4, negative 5, and then 5, negative 4 and 2/3. And if I make those look like a V, because it's an absolute value graph, it should always look like a V. Now we see if our transform graph matches what we said it should be doing. Does it look like we have vertically shrunk or vertically pressed down on that blue parent graph? Yeah, if I push on it and vertically shrink it, that flattens it out to look more like the pink graph. Does it look like our vertex moved right 4 and down 5? Yep, sure does. So it's not a bad idea, if you did want to graph that parent graph, just to make sure that it looks like your transform graph has done the appropriate transformations. So folks, I would just put a star by this problem. There's a lot of good things to study here to make sure you understand how to use transformation rules to graph. I have to see this work on your test. I'm not just going to be happy if you just kind of rough sketch that from your calculator, or even if you get some exact points on your calculator, I got to see the parent table, and I have to see how you transformed it using your rules. Any questions on that one? All right, we got one more problem to do together, and then I'm going to turn you guys loose. We're going to do number 13 together. So on number 13, we are given the transform graph, and we want to try to write the equation for this. These types of problems were the most frequently missed on this test for little details like forgetting to designate what type of function this is. So I look at this graph, number 13, and what type of function is it? It's a cubic function. That means the function that I write needs to have x stuff being cubed. And I think on the quadratic one on the test, I had a lot of people miss that exponent of 2. So y equals x cubed. Now from here, we have to decide what transformations are happening. We've got our left-right sliding transformations. We've got our up-down sliding transformations. We have vertically stretching and vertically shrinking. And we have vertically reflecting it. Now, a lot of times I like to look at the vertical reflection first because it allows me to just check the shape of my parent function. So there's what my parent function looks like. Does it look like we have vertically flipped it so that this part is curving down and that part is curving up? Nope, the shape looks exactly the same. So look at shape. No vertical reflection. So vertical reflections, you just kind of eyeball. Next, I like to look at the sliding transformations. So if my parent vertex starts at 0, 0, or rather my parent central point, where has our central point moved? It looks like it slid 2 units to the right. So right 2. So how do we move our function right 2 units? Is that going to look like x plus 2 in the equation or x minus 2? X minus 2. I'm going to go ahead and put that little cubed in there so that I remember that this is what makes it a cubic function and that negative 2 needs to go on the inside. So then does it look like it has slid down at all? Yep. It looks like it slid down 1 unit, which would be a minus 1 on the outside of the function. So let's just go ahead and start writing this sucker. We've got y equals x minus 2 cubed, and then a minus 1. Ms. Kyra, why'd you leave that awkward space in front of the parentheses? Well, we know that there's no vertical reflection, but we don't know if there's a vertical stretch or shrink yet. So better leave some space there just in case. So to determine if there's been any stretching or shrinking, what we do is we look at the slope from the central point or the vertex to the next exact point. So as I'm looking at this one, it looks like we are going up 2 units and right 1 unit. So our slope, quote unquote, and if you need more details on that, you can look in your note packet. Don't forget, folks, your notes are kind of the slowed down version of what we are doing here. You can find the learning target, look at all those different problems we did, all those little side notes, and that is a great place to study as well. Your note packets are like your version of the textbook. So our slope is rise 2, run 1. So that means we've got a vertical stretch by 2. So I'm going to go ahead and put that 2 being multiplied out in front. And that is our transformed equation. And if I were you, using a highlighter, I would just circle that little cubic part because that's a really easy detail that students forgot about on the first go at this test. So folks, that is all that I want to cover with you guys from Unit 1 and Unit 2 today. Tomorrow we will cover Unit 3 and Unit 4. So the rest of the time is work time, and feel free to work together if you want on this. I'm not officially going to have you guys turn this in, so it's up to you whether you want to do it or not. Bears mentioning there's no retakes on the final, so you get one go at it. So you will not be turning this in for points or anything, but it is the best way that you can study for math.